This morning, assuming you're all awake, and I'll try to be as well, we're going to talk about environmental contamination. I know the title says residues and the public health impact of residues, but because this environmental piece, it doesn't look like there's a whole lot in the program related to resistance as well. I'm going to sort of weave the two together, both resistance and residues, as they flow into the environment. This is not going to be a talk about toxicology. So I'm not talking about whether residues that are excreted into the environment can have some toxicological effect. What we're going to focus on is the microbial relationship with those residues, whether resistance might develop, how resistance spreads, and that being the public health impact. Okay, so this is not going to be a talk about toxicology. So some of the questions we'll try to address. How much antimicrobial residues in the environment? And in that, we're going to start this discussion of how do you even know where it's coming from? How do you start this process of attribution? Is there biological activity of these residues? As you'll see from the various works that have been done on this topic, the residue levels in the environment, let's say in waterways, are extremely, extremely low. Does that mean that they are unimportant? So we'll talk about that. How can we predict how much residue will be loaded into the environment? From an agricultural standpoint, we have to start addressing this issue because it's going to bite us if we don't. And we need to have some understanding of how much environmental loading there is from the ways in which we use antibiotics on the farm and then how they get from the farm into the environment. So I'm going to talk about some approaches that we've been taking to model this. And finally, I'll finish with since this is a One Health meeting, sort of an example One Health approach that we have been doing again in Chile. I mentioned yesterday I do a lot of work in South America, and the kind of program that we're putting together there. So let's just start with this Confusogram, this ecological model of how things move around and get back into the environment. You know, we always see these schematics and they seem to make sense with the way the arrows move. We always can find limitations in them, but basically, to sum this whole thing up, everything's connected, right? It's one system. It's an ecosystem. What we need to be thinking about is what is our role as, let's say, in agriculture? What is our role as public health managers, as people who operate wastewater treatment plants, as raising crops, whatever it is, let's say even taking your own antibiotics at home and deciding you have extra, so what do? You flush them down the toilet. How do all of those things come together to ultimately impact the environment? A little more simple, I guess, schematic might be this one that appeared in 2003 from Kummer, who's done a lot of work on antibiotics in the environment. And really it's talking about, so you start with this production of the antibiotic itself. There are studies out there looking at the effluent coming from these the factories that are producing the antibiotics, and their effluent is loaded with residue. Then you have the use, there's sewage, there's manure, there's runoff, etc., and ultimately it might end up either into the environment, in the soil, let's say, or into our water supply. I think where this topic, for me at least, really started becoming, well, it came to the forefront, was this paper that came out in 2002, which was really a USGS survey, US Geological Survey, sites throughout the country looking for levels of various compounds in our waterways. And before this, I just don't think that we were paying that much attention to it, at least from the standpoint of these health concerns. And what they showed, and this is just this let's say a box and whisker plot or of levels. And I've circled, this is a study that looked at pharmaceuticals, hormones, or other contaminants. I've circled some of these, what we would consider antibiotics, like on this far left circle is triclosan, probably not a whole lot of agricultural use, but perhaps because we know how much it's used in humans, if we knew how much triclosan was in a sample, maybe that can help us attribute back to a human health source. We've got trimethoprim being the next one circled, erythromycin, lincomycin, sulfamethoxazole. So you have these compounds that they're looking at, and the key is to look at this axis. It doesn't really matter what compounds we're talking about. They're all out there. But the levels we're talking about are in the 0.1 to 1, maybe up to 10 micrograms per liter. Okay, these are really, really low levels of compound. And I think when this came out, there were some that said, wow, oh my gosh, everything is in our water supply. And others said, yeah, but look at those levels, it's irrelevant. So which is it? Should we be concerned? Is there any biological activity there? Is there any potential health impact, either to animals, to humans? Are we medicating ourselves just by drinking our water supply every day? So then there's been a series of studies since that have gone on and looked at very specific locations, for instance, at wastewater treatment plants. And in general, what these studies show is that when flow levels, water flow levels are low, the concentrations are higher. Makes sense. So now you should be thinking seasonality. Is there a season when we are more at risk? The things that we do, if we're trying to think about connectedness and what we're doing on a farm, runoffs, etc., if we're seeing that we're loading the environment in times when water levels are lower, we're going to see higher concentrations if the compound can make its way into the water supply. And I'll get to some of the nuances of that in a little bit. Temperature plays a huge role in how fast these compounds degrade. The lower the temperature, the slower the compound is going to degrade. Sunlight plays a key role. There's issues of organic binding. These compounds can actually bind in the environment, and we have no idea how long that they'll persist, what their half-life will be once it goes into that state. So there's a lot that these studies started to show that should raise some concern. There's others, like this one, that we're looking at effluents from hospitals and households that actually tried to relate the concentrations that they were observing back to what might be an MIC-type concentration. And when you were at these effluents, like around hospitals, these concentrations for some compounds were above MIC levels. These weren't our just standard survey of some waterways finding 1 to 10 micrograms per liter. Quantities ended up being a lot higher in some of these effluents. So is there a pressure? Is there a human health impact? Very likely. Okay, so what do we do about that? Is there actually any regulation? And that word scares a lot of people, but if you looked at a hospital effluent and you asked, well, are they required to get these levels of compounds down to a certain level? And the answer is no. So let's go into a few studies, or I'll start with this one in particular, that tried to put a lot of this together now with understanding the relationship over space. A lot of these other studies were just surveys. They went out and took some random, I won't even call them random, haphazard sites and asked how much of a compound can I find at those sites. This study actually had a design. What these authors tried to do was they went in Colorado in a watershed and designed a series of sampling sites that would include what they called a pristine area, so very little human impact, into an urban area where you have now wastewater treatment plants, and into the agricultural area with some urban where you have potentially runoff. I don't think I put any of their tables on here. But what they showed, again in summary, was concentrations were higher at times when flow was low. They found what might be considered animal-type antibiotics, predominantly around the agricultural areas. And they found what you might call human compounds, human-use compounds, predominantly in these urban areas, like around the wastewater treatment plant. Okay, seems to make a lot of sense. Except, and where I always struggle with these kinds of studies, is, again, it goes back to attribution. If you took a sample, the river flows continually all the way down into the ag area from the urban area. If you find a compound that could be a mixture of both human use and animal use down in the ag area, how do you know who's the source of it? Does it matter? It's not a blame game. We need to understand what impact, what role different uses that all funnel into our water supply are having. How do we begin to do that? And mathematically, there might be some ways of doing attribution, but I haven't really seen those studies yet. So instead, what we tend to do is say, well, this sample was taken at this location, so I'm going to assume that what I find in the water supply at this location came from the activities closest to that sample. And I don't think that's a fair way of taking this, an approach to this problem. The other problem that I had with this study was you had this nice spatial data set. You had these sites going all the way down the river. And you could have done this assessment to understand what is the relationship over time and over space of these sites. And instead of using some formal spatial statistics to actually get at these questions of what's the actual relationship, can you predict one site from another site, they just did some very simple correlations and didn't really dive into the data like they could have. So that takes me to, this will be the first segue into my work in Chile. For those of you who don't even know where this is, Chile is in South America on the west coast, and it is an incredibly long country. And where I work is mostly in the south, so it would cover this area down in here. And I'm going to use it in various parts of this talk today, mainly because over about now 10 years I've put together what I consider sort of a One Health, even though it never was called One Health, but let's say an ecosystem-based approach to understanding health, environmental health, human health, and animal health. So in this area, so there's a city here called Valdivia. It's the capital of the region. It's known as Región de los Ríos, which is region of the rivers. And what you have is, it's just beautiful because it goes from the mountain lakes up in the Andes down to the ocean very quickly, and it's made up of many, many river systems. And so they face some of the same issues. You've got all sorts of uses and impacts along this river system. You've got agriculture, you've got industry, like let's say they've got pulp plants, they're putting out effluent, you've got hospitals and wastewater treatment plants, you've got perhaps sanitation systems that are not ideal. So all along this riverway there are impacts. How do we start to assess the relative importance of those, and how do we protect their water supply? So I'm just going to go through quickly a study we did. This really was around 04-05 that led us to sort of moved me forward in my thinking about how to address this ecosystem. We had in this area, so going back to the, I'll jump to here. We had about 40 sampling sites along these rivers that feed into the city of Valdivia. What we did was we sampled 12 of the dairies that are located right on that river. And we sampled about 40 other water sites that covered various impacts from human use. They could have been around the wastewater treatment plants, etc. And what I wanted to know was really starting here, so here's our wastewater treatment plant, here was one of the dairies, would be, and yeah, that's not Minnesota, would be what is the relationship in the microbiological diversity that you would see from the farm samples to the river samples. These dairies are right on the river, and people are always talking about runoff. Well, I thought, okay, at this point I can't do residue testing, but maybe I can use some indicator organisms to get some idea of the relationship between the ag on those rivers and what microbiologically we're finding in the rivers. And I think some of that type of an approach will come up in the next talk from Dr. Reed. And what you're going to see in this table, the numbers don't matter. These are the median zones of inhibition. All I really care about is that you see that there are rows and that there are blue shaded cells. The blue shaded cells would be antibiotic concentrations that are resistant to using clinical breakpoints with zones of inhibition. Okay? Each one of those rows represents a cluster of isolates. So these are E. coli. And when they have a certain resistance pattern in common, they end up going into a cluster together. So we have clusters A to F in this first row, if you can't read A to F, just the very top row. And these are our pan-susceptibles. So I don't even bother separating them out into A, B, C, D, E, F. They're all pan-susceptible, so they all get lumped together. And you can see the numbers so over to the right, there's a rivers column and a farms column. 318 isolates came out of rivers, 736 out of farms. They're all mixed together. There's really no separation of the isolates that are pan-susceptible. When you get into the antibiotic resistance profiles of these E. coli, so go into these blue shaded areas, let's start at the very bottom and work our way up. Cluster O, where there were only 3 isolates, was resistant to every drug we tested. And those 3 isolates came from the dairies. We never found them in the water. Go up to N. You have a different resistance pattern, 7 isolates covering a range of sites along those rivers, never found on the dairies. And then it just keeps going up. It goes, if you count these clusters, M, 0 from the rivers, 8 from the farms. There's a little bit of mixture in L, in K, 0 from the rivers, 28 from the farms, and vice versa. We saw so little overlap between the isolates that were coming from these dairies and the isolates we were finding in the water supply. And yet, if I looked at a temporal and spatial correlation, the isolates that I was finding downstream, I was always finding in the hospital effluent upstream. And it got me thinking, how, there's no way that if I found a multi-drug resistant isolate near a dairy that anyone would say it came from the hospital. They would say it came from the dairy. So how do we do this better? How do we get at this question of how to attribute sources when it comes to things like environment and spread? And then how do we know if any of this resistance we're observing could be due to practices at those sites? The use of antibiotics in the hospitals, the use of antibiotics on these farms. These farms definitely use plenty of antibiotic. These dairies, I'll just leave it at that. And so what we were also able to do then is start to map out the spatial distribution of the farms and the river sites along with the clusters of isolates that you see and start looking for these spatial relationships. And I'll get back to that a little bit later as I talk about a model for a possible One Health approach. So as we're doing that study, and I said one of the questions we had is, what role could these antibiotics be having? So then we ended up thinking, well, maybe we should test that. Because if you go into the literature, it's really hard to find papers that have actually tested the biological activity of antibiotics at the concentrations you find in water supplies, where we're talking 1 to 10 micrograms per liter. I was shocked, actually, that I couldn't find anything, really. And so, and then the question becomes, well, how are you going to even do this? How do you test the selective pressure that an antibiotic has in the water supply? What system are you going to use to mimic that? What we did was we used these chemostats or bioreactors in the lab where we took Mississippi River water. Again, this study was all done in Minnesota. And you put it in this continuous flow system. You're feeding it low levels of some nutrient to keep the bacteria alive. But the problem is after 1 or 2 days of this, the composition of the bacteria in your chemostat have completely changed. It doesn't look like the river anymore. First of all, it's getting lots of oxygen. So anything that's in the river that might be in the low oxygen areas of the river, well, they're not going to survive. As well, you definitely are going to see changes in the microbial composition. So this is an in vitro, a lab-based study, and may not reflect what actually is happening in the river. On top of that, it's water only. We didn't have sediment, so you're not dealing with any of the organic binding that might happen. But we didn't know how else to start because we really hadn't seen anything out there for testing this. So what we did is we set up many replicates of this experiment using 2 different antibiotics, so each one done in separate replicates. We looked at chlorotetracycline and we looked at tylosin. Why? Because both of those are found in these environmental surveys. Both of them are relevant from the agricultural perspective. And so what we did on the chlorotetracycline is we used levels like 8 micrograms per liter, which would be a level that you might find in these water surveys, 800 micrograms per liter, and all the way up to 32 micrograms per mil, moving into now a range where you would actually be using it, let's say, at a therapeutic level. And for tylosin, it was in the low range, let's say around 10 micrograms per liter, all the way out to about 50,000 micrograms per liter. And this is going to be dosed into this chemostat twice daily for 10 days. So it's continually being fed with more nutrient to keep the bacteria alive. And just to quickly show you some of these results. So this is on the chlorotetracycline side. And on the top graph, it's total bacterial count. So these are gram-negative bacteria growing in the presence of chlorotetracycline in the chemostat. And what you can see is that on that top graph, this is total count. The chlorotetracycline in the water didn't have an impact on the total number of bacteria in that chemostat over time. Possibly that green line, which is the high dose, 32,000 micrograms per liter, decreased the bacterial count slightly. Where you see the effect is in the second graph, where we looked at now how much resistance was selected for, so bacteria with chlorotetracycline resistance. And what you see in those top 2 lines are the 32,000 and the 800 microgram per liter chemostats, significantly different than the control and the 8 microgram per liter chemostat. What does all that mean? The low dose that you'd find in the water supply, like 8 micrograms per liter, did not select for resistance. It didn't look any different than the control, which had no antibiotic. So it makes us question whether chlortetracycline, at least, has any impact at those levels on bacteria in the water supply, whether it can actually select for resistance. Because in our studies, it didn't. Now, again, there were caveats, and this is only looking at the gram-negatives. There's a slightly different picture, though, that we get from looking at tylosin, and it gets much more confusing. On the tylosin side, what we're going to be doing is looking for gram-positive activity. So we're culturing this on a CNA plate, looking at the gram-positives. And on the top graph, what you see is the total bacterial load. And there is a dose response here. The control had basically no effect over time, a very slight effect from the 10 microgram per liter, and a greater effect for the 50,000. And this is the statistically weighted average after running, this was 6 replicates. But you see no significant difference when you look at the counts, the second graph, of tylosin, of agar that contains tylosin. So this is looking at what fraction of the population, what was the count, let's say, of bacteria with tylosin resistance, assuming that you can actually define that, and there didn't seem to be this same difference. It seemed to be that the tylosin was having its biggest effect on knocking out some of the gram-positive population. However, when you look in this top graph at the ratio of resistant to total, or resistant to susceptible, actually, there seemed to be that dose effect, that the higher the dose, the more it changed the ratio of resistant to susceptible over time. So there did seem to be some effect of tylosin in the water on selecting for resistance to that compound. What was even more interesting for me, though, was we know that some of the resistance mechanisms that are out there for tylosin are also, they reside within that bacterium with resistance to tetracycline. They're in the same bacterium. So what we did with these water samples is we also plated them on an agar that would pull out many more bacteria, and we looked for resistance to tetracycline. Now, this is a tylosin experiment, but what you see is that in the high tylosin chemostat, we saw a significant change in the resistance of chlortetracycline. Okay, not in the control and not in the low level, just at these high levels, 50,000. But showing that these high levels could be co-selecting, like I talked about yesterday, for resistance to both tylosin and chlortetracycline. So as we start thinking about what compounds are going into the environment, we need to be thinking about the possibility that you're selecting for more than just that one resistance to that one class of antibiotic. And I'll show in a couple slides here, again, why that is relevant. Some studies in this area have been done recently out of Washington State. This was a paper that came out in 2011. And it was looking at various antibiotics that might be used in agriculture and if they stay active in soils. The issue of activity, again, is really tough to do. These are some in vitro studies where they try to simulate some environmental conditions with soils and manure and other things. And what you find is that there are certain antibiotics that degrade very quickly. So this is a graph showing this effect. And so the higher the line means that the antibiotic was degraded, that the bacteria were able to grow again. If there's no line, it means that the antibiotic residue stayed active and suppressed completely the growth. So on the left, the ones with no lines, you're talking about florfenicol and the cephalosporins. They stayed active for very long periods of time. If it was cold, they stayed active for even longer. So that started, for me, to raise, again, more concerns about cephalosporins, florfenicol, and I'll show why. On the right, you've got tetracyclines, the fluoroquinolones. Those are being degraded very rapidly. Okay? Could basically the tetracycline piece be part of the reason why we saw no effect in that chemostat with chlortetracycline? The only problem is we were continually dosing it, but if that decline is so rapid, it may just not have had any effect when it gets diluted in the water. So again, I'm going to go back to Chile. I've done a lot of work with salmon production in Chile. Now, it's not the easiest industry to get in with. It's taken me many years, but we do have the confidence of some of the producers. And whether it's salmon production in Chile or aquaculture anywhere else in the world, how do you medicate the fish? You medicate the feed, and you put it directly into the water. You can't keep it in some nice place where it's not going to end up in the environment. You're putting it in the environment. And what is one of the compounds approved, at least in many parts of the world, in aquaculture? It's florfenicol. We know that in the salmon production of Chile, they do use fluorphenicol frequently to treat various diseases. So now you're putting fluorphenicol that's medicated directly into the environment, and as this graph shows, that's going to stay active potentially in the environment for a while. But some of us would say, yeah, but fluorphenicol, it's a veterinary-only drug anyway. Okay, let's go back to the figure I showed yesterday. This is that multidrug resistance plasmid that we've sequenced. This came from the dairy cow in Illinois. We have another one that came from, that's almost identical, from the dairy cow in Chile. And again, remember that this one plasmid in one E. coli has resistance to fluorphenicol, tetracycline, streptomycin, sulfonamide, ceftiofur, aminoglycosides, more sulfonamide, and then it's also got quaternary ammonium resistance, mercury resistance. It's all on there. So what effect would the fluorphenicol have if it persists in that water supply for a while once you medicate with that feed? We don't know. At least I don't think we know. What we do know is this table, which again is very busy, and I don't want you to read it, this is a list of isolates that we have cultured out of the salmon production farms that we've worked with, where we've looked for fluorphenicol resistance and asked whether they had the key gene that confers resistance to fluorphenicol, and that gene is called the flow gene. And we find it in many, many isolates in salmon production. The reason I put up this busy table is because you'll see the diversity of bacteria that harbor that gene. Okay? Now, again, I'm not going to put a cause and effect. I know that this gene is in the environment and has been there even before fluorphenicol was approved. But I can't, I'd be hard pressed to say that at least some of this must be related, at least, to the use of fluorphenicol, whether in aquaculture or in other situations. As an aside, I've done work with some hospitals in Chile as well, where yesterday we heard about Acinetobacter baumannii, this isolate that causes problems in human hospitals. We've looked at this isolate over time in Chilean hospitals, and you know what? It's got resistance to fluorphenicol with that gene. Now, how did this human hospital isolate end up with that gene? Now, that's a whole other story that we're still trying to piece together. But again, it emphasizes this being one connected ecosystem. We can't just exist in isolation and say that what we do on a farm isn't going to have any impact in this broader way, nor can we let other, I'm going to speak from an ag perspective, we can't let those who work in hospitals say that what we do has no impact, let's say, on farms. I mean, sometimes you'll hear this question, well, I guess maybe something could get back to the farm. Give me a break. It's one system. Everything is flowing from the farm to the environment and back onto the farm again. So then this group from Washington State just put out this paper, it just came out actually last week, about the use of ceftiofur and how much of it is being excreted in urine. Now, many of us have focused on excretion profiles of antibiotics in feces. We don't talk a whole lot about urine. And yet, for this compound, we know that the majority of it is actually excreted in urine. And a lot of that should be bioactive based on some of the profiles that we've seen in the literature. So this group wanted to get some understanding of what might be that level of activity and what factors would influence its activity. So again, the lower the temperature, it might have less activity. So this is growth. The higher the bar, the more the bacteria can grow, so the less active the compound. You see that the 4 degrees Celsius bar is much higher than the 23 Celsius, so lower temperature, the presence of organic compound degrades it faster, things like that influence the speed with which we can expect the compound to decay in the environment. But it's there, and it's being put out in potentially large amounts. This is coming out in the urine. How do we know? How do we start to predict what we are doing on farm as it relates to the loading of compound into the environment? And I feel that if we don't get ahead of this and really take the initiative to show that we are serious about it, we will get blamed in agriculture for just either ignoring the issue or causing a problem. We want to be on the forefront of saying, we know that this could be an issue, and we want to show what fraction of what's being loaded into the environment might be attributed to us, and we are working on interventions to reduce those risks. I really believe that we have to get ahead of this one. And so here's one example of something I've been doing, which is trying to model how these compounds get excreted. I'm going to use a dairy example because I'm doing some modeling mostly in dairy right now. How do we get estimates of the environmental loading of antibiotics getting excreted? And the problem is, and this is because, as you'll see, the paucity of data that are actually out there I had to take two different approaches. For some compounds, you can actually track the amount of compound that goes into different compartments within the animal. So let's say you inject a cow with an antibiotic. Some antibiotics, we have data that says how it's going to be distributed into different compartments and then make it into the feces, the urine, the milk. You can actually, if you have that information, you can get an idea of what the Cmax would be, so the maximum concentration in each compartment. You know the half-life in each compartment. You know the volume of urine or feces that gets excreted. And you can now model the amount of compound that that cow will excrete into the environment. And then there's various other equations to estimate how long it will persist in the environment. The problem is, initially I thought, well, this is going to be pretty easy. There must be all this data out there. The shocking thing for me was that the older compounds, which we would think by now we would have this information, actually have the worst data of all. I can't find data for a lot of these compounds. All I know is the total amount that you dose, the total amount that and maybe the fraction that goes into the different compartments, but nothing about the decay, nothing about the concentration that would be the maximum. So basically I have to back calculate a lot of things to get those concentrations. So hopefully, if these kinds of data are important, we'll be designing studies to get some idea of how compound is metabolized and excreted by the animals we treat. So what we've done in these modeling exercises is using different compounds, and I've kept this completely generic. It doesn't say anything about which compound. There's no axes, so you can't even tell doses, because right now I don't want you to have any of that information. I just want you to understand what the data gaps are and how I'm approaching this. But this would be, let's say, a 5-day treatment in a cow, and I can model, this would be fecal excretion and fecal concentration, how much compound and what fraction of that is active is being excreted over time. I can also look at the milk excretion. Why does this become important? Because we face this issue of what do we do with the waste milk? If you're within that withholding period, what are you going to do? Do you discard it, which means you're dumping compound antibiotic directly into the environment, as well the farmer probably doesn't want to waste it? Or do you feed it to the calf, which means that now you're dosing an animal with active compound. So you're furthering this selection pressure in an unintended way. So we have a dilemma. You're going to have to do something with the discard milk. So part of the reason that these models now include this waste milk excretion is because now I'm going to feed it back to the calf. Let's say the calf is feeding twice a day, which is why you might have 2 spikes there. and then we can start to predict how that compound is going to be excreted from the calf. What these models don't yet account for at all is what role does an oral dosing of a calf have on the gut bacteria? Are we selecting for resistance in the gut calf when we feed that discard milk? And this is just one of the many scenarios that we'll face in ag. And we can try to say that, well, you know, in general, a lot of people don't even realize we do this, so let's just ignore it. You know what? In Europe right now, the discard milk issue is becoming a huge issue. And it will be here as well. We really need to think about, again, how do we get ahead of the curve? How do we really understand what impacts the farm practices that we have on the environment? What we found by doing that kind of a study was, again, I can't believe how few data are actually available to estimate the concentration of these antibiotics that you would find in those various compartments. Feces, urine, milk, the compartments that are going to go directly into the environment. We may have good data, PD data on getting the drug to the site where the infection is, but we don't seem to have as good of data on how the compound actually gets excreted. And the older compounds, the data sets seem to be even worse. Again, if environmental loading is something of interest, so we actually want to understand how our antibiotic applications impact the environment, I think we're going to have to be designing additional trials just to get those simple data, things like Cmax and half-life, etc. And again, the dairy example for me highlighted this discard waste milk issue and that dilemma of what you do with it. All right, so for the final piece, I'm going to now move into just how I've tried to put all that together and probably in an extremely naive way say, I'm going to approach this from a One Health perspective, and we're going to do it. And we're going to do it in Chile because, A, I have a lot of infrastructure there. B, I think that on some of these issues, it's easier for me to put together a team, and you'll see in a second why. So to set the stage, I'm going to use this example first as a theoretical model that we put out, just asking about the interrelationships that exist across a landscape. If you look at the environment and you start to put onto a map all the things that can exist, this is actually one of the maps we use in Chile, this is the river systems in our area, and you start to map out where are my dairies, where are my farms, where are my hospitals, where are the wastewater treatment plants, you start to build this model of connectedness. Okay, I believe that that's one place we have to start. We need to understand the spatial relationships of all of the ways that we are impacting that environment. And we've started to do that, again, in this region of Chile. The reason that the map is now shaded is because one of the things I'm also concerned about, if you remember on that plasmid that I showed, there was metal resistance, like mercury, and let's say quaternary ammonium compound. There's also copper resistance. Copper is a fairly common thing to find resistance to on some of those plasmids. What is Chile? Well, you may not even know this, but one of the products they're most known for is copper. And in many of their environments, you can find copper concentrations that would be at the levels you might think about having an actual effect. Now, is it freely available copper that could actually select for resistance? I don't know. I don't know anyone that's actually looked for it. But so a question, and the reason I shaded this is, do we even need to understand what the environment has already? Things like copper concentrations that might be selecting for resistance regardless of what we do with our antibiotics. Right? It would be really easy to say if all of the dairy farms were in the high copper area, and you find resistance to antibiotics that happen to also have resistance to copper, to say it must be the use of the antibiotics on the farm, when in fact it could be the underlying distribution of the copper. So what I am trying to piece together here is really this complete approach to how you think about the evolution of resistance from both the impacts that we have on the environment as well as the impacts that are naturally present. And the reason it becomes important is because it can dramatically affect the inferences that you make. Let's say that you look at that blue line there that I call baseline, which says that that is the rate that you would expect resistance to rise if you knew everything about the environment that I've shown in this picture. But if you know less information, you don't really know the distribution of the copper that's affecting things, or you don't really know how much antibiotic is used on one farm versus another. What the model that we developed showed is that you could be dramatically underestimating the pink and the orange lines, or even overestimating the green line, what impact an antibiotic use on a farm actually has. A lot of people would say, you know what, there's this epi term called a bias towards the null, which would say that you're usually going to end up making an estimate that's less important, like, does the antibiotic cause resistance? Well, you're going to end up underestimating its effect. No, the model shows you could either overestimate it or underestimate it. You're basically just going to get it wrong. You really need to understand all of the aspects that affect resistance at a given location if you want to accurately estimate what role antibiotics play. And that includes antibiotics in the environment. So we've tried to take that idea, which was put out, I think it was 2006, as a theoretical model, and now try to put this into action. So basically for the last 5 to 6 years, I work in this region, and I've been working with a variety of stakeholders to put together a team to address this issue from an environmental perspective. The great thing about this region, again, is that you can start up in the Andes in these lakes. They funnel all the way down through the river systems, and then in the lower right is actually the capital of the region, Valdivia, where they have an active fish market. It's right on the river. It has some similarities to, let's say, like a Seattle. And so there are an incredible number of impacts along the waterway. We've done plenty of studies as well of how the people use their environment. We've looked at things like manure management of the person on the top left, that's actually, she's taken her water sample for drinking water. So you have this very tight relationship with their own environment. And this is another reason why we felt it's really important to get a handle on the things affecting the water supply in this region. that is actually protecting sort of someone's water supply on the right, top right. What we have found, again, are some of the same factors. The colder the weather, the lower the water flow, the higher the concentrations of things you find in the environment, like these antimicrobials. And so what we've done, and this is really my last slide before I conclude, and I'm incredibly nervous about this. We have a meeting set up for January 2013 in this town just up the mountain a little bit from Valdivia, known as Panguipulli in Chile. And we're putting together a team mostly from the regional perspective that will include the Ministry of Health, the Ministry of Ag, the Ministry of the Environment, Tourism, indigenous peoples. This is an interesting piece. We did a study a few years ago that the indigenous people of Chile are known generically as Mapuche. Mapuche is actually a very specific group, but in general you'll just say the Mapuche. And they have a very different need when it comes to water issues. They have what they call the sacred sites. And the water quality at their sacred sites, or any other the water that they use, is not even surveyed by the health department. They're just, some people know where those sacred sites are, but they're never actually evaluated. So we went in and looked at whether the health department was meeting the needs of the Mapuche, of the water quality issues, and what was the water quality at their sacred sites. The government occasionally says, you know what, we want to put something on your sacred site, so we're going to move you to another water over there, because that water, that could be sacred too. You know, and so they have fought. There's actually some very violent fights that happen. But we're going to put them at the table because we think it's important that their needs are also met. We've got the National Water Authority, so that's all on the left, these various government-type ministries. On the right, we've got some NGOs that are coming, private foundations as well as businesses. So on the business side, you've got the pulp plants, you've got lots of factories. They're influencing the water supply directly. We've got the Salmon Coalition that's going to be present because they do raise salmon in some of these riverways, as well as academics like myself. I work with hydrologists. And what we're trying to build is a river, basically a hydrological flow map of the region that shows where all of the impacts are, all of the uses of the water supply in the region, as a way to start building a risk model. How do you think about sustainability when you've got so many competing pressures on that water supply? I mean, this is something to me that is not a 1, 2, or even 5-year project. This health department that I work with has had the foresight to say, this is something we want as a model. We think we could even be a global model, and we're willing to put this investment. It helps that in these private foundations, like you've got Amigos de Panguipulli, which include like CEOs from Banco de Chile and places like that. So hopefully we can convince them at this meeting that this is worth investing in. And this is the One Health model we're taking in this area. All right, so take-home messages from this talk, because it probably wasn't exactly what you thought it would be. One is that we can't ignore these environmental concerns. And I really feel that we are ready to take the lead on this. Waste management is going to be a key issue, and we are the ones best suited to study it. We don't want to wait until someone else comes in and tells us about all the things we're doing wrong. We can identify where the data gaps are and how to fill them. This issue with residues, well, in general, the residues decrease with time. That's just a function of what they do. There will be some rate of decay, but that rate of decay is going to vary by things like temperature, organic compound concentration, and all sorts of other things. We need to get a better handle on what those factors are and how they influence our waste management. The biological activity piece still, in my opinion, remains highly uncertain. I mean, it may turn out that most of these concentrations really are irrelevant, but we need to know that. The excretion data from animals is lacking, and that just, to me, is sad, and I hope that we can do better at that. If you think about these compounds, again, they can bind in the environment. That can be analogous to things like the way they bind in the gut, they bind in the serum and the plasma. These residues bind, and we have no idea what their half-life becomes once they become organically bound. And I guess the most important thing for me in this is it can't be a blame game. I know that on the ag side we are often on that side of being blamed, but what we're trying to do here is minimize the impact of residues on health. Environmental health, animal health, human health. We know that we play a role because we are tightly tied to the environment. So let's take the lead on how you do this kind of thing and develop methods for how you attribute what our role is versus any other of the uses that exist in that environment. With that, I'll thank various people that were part of this talk. And again, for full disclosure, I've had funding from agencies like these, and I have worked with companies like Bayer, Pfizer, Elanco Animal Health, and again, I'm proud of those collaborations I've had with industry. So.